What if I told you that everything we see, every star, every galaxy, even the vast emptiness between them, is being pulled towards something we can't see, something beyond the edges of our known universe? This isn't science fiction. It's one of the most baffling mysteries in modern cosmology, a phenomenon so strange, scientists call it the dark flow. Picture this: hundreds of galaxy clusters, each weighing billions of suns, all streaming in the same direction at staggering speeds, as if dragged by an invisible hand. And here's the unsettling truth: no one knows what's pulling them. This is the kind of mystery that rewrites textbooks. For decades, we've mapped the cosmos, confident that the Big Bang set everything in motion. But dark flow defies that logic. It suggests forces at work we never imagined, hidden structures, perhaps other universes beyond our own, exerting a gravitational tug so immense it bends the fabric of space itself. Imagine standing on a shore, watching the tide rush out, only to realize the ocean isn't retreating, it's being sucked into the unknown. That's the scale of this enigma. And that's exactly what we're diving into today: 30 facts about dark flow that will challenge everything you thought you knew about the universe. From the eerie patterns in cosmic microwave background radiation to the daring theories about parallel realities, we'll explore how this phenomenon could upend our understanding of physics, gravity, and even reality itself. So buckle up, because by the end of this journey, you won't just see the stars differently, you'll question what lies beyond them. The story of dark flow begins in 2008, when a team of astronomers led by Alexander Kashlinsky made an accidental discovery that would send shockwaves through the field of cosmology. While studying data from the Wilkinson Microwave Anisotropy Probe, a spacecraft designed to map the faint glow of the Big Bang, they noticed something impossible. Hundreds of galaxy clusters, each containing thousands of galaxies, were all drifting in the same direction at nearly 2.5 million miles per hour. This wasn't random motion. It was as if an invisible river in space was sweeping them toward some unseen destination beyond the observable universe. At first, the team doubted their own findings. The laws of physics tell us that after the Big Bang, matter should be moving in all directions like fireworks exploding outward. But these clusters weren't just drifting, they were racing together like iron filings pulled toward a magnet we can't see. To confirm the anomaly, Kashlinsky's team spent months cross-checking data, ruling out instrument errors or local gravitational effects. The evidence was undeniable. Whatever was tugging at these clusters wasn't just massive, it existed beyond the cosmic horizon, in a place where light hasn't had time to reach us in the 14 billion years since the universe began. The implications were staggering. If dark flow is real, it means our universe isn't just expanding, it's being pulled by something outside it. Some theorists suggest it could be the gravitational influence of another universe brushing against ours, while others propose an unfathomably large structure lurking in the unobservable darkness. One thing is certain: this discovery shattered the long-held assumption that the cosmos is uniform on the largest scales. The universe, it seems, still has secrets we're only beginning to glimpse. Here's what makes dark flow truly mind-bending: those galaxy clusters aren't just drifting aimlessly. They're racing toward the Hydra Centaurus supercluster at speeds topping 1,000 kilometers per second. To put that in perspective, that's over 3,600,000 kilometers per hour, fast enough to cross the entire United States in less than 4 seconds. And here's the kicker: this motion shouldn't be happening. The universe is expanding, yes, but according to the Hubble constant, that expansion should be carrying galaxies apart in a roughly even, predictable way, like dots on an inflating balloon. Instead, dark flow shows entire clusters being yanked off course, like leaves caught in a cosmic riptide. Even stranger, the direction they're moving, toward Hydra Centaurus, doesn't align with any known gravitational source powerful enough to explain it. Our best maps of the observable universe show no structure massive enough to pull thousands of galaxies at once. So what's going on? One theory suggests these clusters might be feeling the gravitational pull of something beyond our cosmic horizon, perhaps a neighboring universe or a colossal, unseen mass left over from the chaotic moments after the Big Bang. It's as if we're standing in a valley, feeling a wind no one can see, tugging us toward mountains hidden by fog. The sheer scale of this mystery forces us to confront a humbling possibility. We might not just be mapping the universe, we might be glimpsing the edges of reality itself. One of the most compelling explanations for dark flow points to something lurking beyond the edges of our observable universe. Structures so enormous, their gravitational influence reaches across cosmic distances we can't even see. Think of it like this: if our observable universe were a campfire's glow in an infinite forest, dark flow might be the wind we feel from a hurricane raging just beyond the trees. Scientists suspect these invisible forces could be leftovers from the universe's earliest moments, when the rapid expansion known as inflation stretched spacetime like taffy, potentially creating uneven ripples in the fabric of reality itself. Computer simulations reveal how this might work. When researchers model the early universe, they find that tiny quantum fluctuations during inflation could have snowballed into vast, dense regions lurking beyond our cosmic horizon like mountain ranges hidden in a fog. These structures would be unimaginably massive, potentially weighing hundreds of times more than the entire visible universe. Their gravity would reach into our observable space, tugging at galaxy clusters like moons caught in a planet's tide. The eerie part, we'd never see them directly because light from those regions hasn't had time to reach us in the 14 billion years since the Big Bang. Some theorists take this even further, suggesting dark flow might be evidence of a multiverse. Imagine neighboring universes, each with their own physical laws floating like bubbles in a vast cosmic foam. If one of these bubbles brushed against ours, its gravitational pull could explain the mysterious motion we're witnessing. It's a wild idea, but not impossible. Certain models of string theory actually predict such interactions. Of course, proving it is another matter. Without direct observation, we're left piecing together clues from the only evidence we have, those hundreds of galaxy clusters, all rowing in unison toward some invisible shore. What makes this theory so revolutionary is how it upends our understanding of the cosmos. For centuries, we assumed the universe was roughly uniform, that no single direction held more significance than another. Dark flow shatters that assumption, hinting at a reality where our observable universe might just be a small neighborhood in a far stranger, vaster metropolis. And if we're being pulled by something out there, it begs an even deeper question. What else is hiding beyond the light? To uncover the secrets of dark flow, scientists turn to the oldest light in the universe, the cosmic microwave background, or CMB. This faint afterglow from the Big Bang blankets the sky, and buried within its subtle temperature variations lies a crucial clue. When researchers analyzed this primordial light, they noticed something extraordinary: a faint but consistent shift in temperature aligned precisely with the direction of the streaming galaxy clusters. It was as if the universe itself had etched an arrow pointing toward whatever was pulling them. The data revealed a pattern so specific, the odds of it being random were less than 1 in a million. Imagine looking at a weather map showing raindrops falling in perfect unison toward a single point on the horizon, except here, the raindrops are fluctuations in temperature dating back nearly 14 billion years. This anomaly, known as the kinematic dipole, shouldn't exist if the universe were perfectly uniform. Yet there it was, a statistical fingerprint of something massive yanking at the fabric of spacetime. Not everyone was convinced, though. Skeptics argued that instrumental errors or local galactic movements could mimic the signal. Teams using different telescopes, like the Planck satellite, initially reported conflicting results, fueling debates in cosmology circles. But when independent studies kept corroborating the original findings, with some measurements showing galaxy clusters moving even faster than first thought, the evidence became harder to dismiss. The CMB wasn't just background noise anymore. It was a cosmic breadcrumb trail leading to one of the greatest mysteries in modern physics. What makes these temperature shifts so remarkable is their scale. The variations amount to mere millionths of a degree, yet they trace a flow spanning billions of light years. It's like detecting a whisper in a hurricane and realizing it's carrying the coordinates of some unseen force. And the implications ripple far beyond dark flow itself. If these patterns hold, they could mean our universe isn't the only one feeling this gravitational tug, that whatever's out there is so immense, its influence bends not just galaxies, but the very afterglow of creation. Long before dark flow stunned astronomers, another cosmic mystery lurked closer to home: the Great Attractor. This enigmatic region of space, roughly 250 million light-years away, exerts such a powerful gravitational pull that our entire Milky Way, along with thousands of other galaxies, is being dragged toward it at over 2 million kilometers per hour. At first glance, these two phenomena seem eerily similar. Both involve vast collections of galaxies moving unnaturally toward unseen forces, but the scale of their influence reveals a chilling difference. While the Great Attractor's reach stretches across hundreds of millions of light-years, dark flow's grip extends far beyond, pulling galaxy clusters billions of light-years away. Distances so vast, they eclipse the Great Attractor like a tidal wave dwarfing a ripple. Here's what's even stranger: their motions don't align. The Great Attractor tugs us toward the constellations Norma and Centaurus, while dark flow's current drags clusters toward Hydra Centaurus, nearly perpendicular in the cosmic map. This misalignment suggests something even more profound: that these might not be separate anomalies, but pieces of a larger, unseen structure warping spacetime itself. Imagine standing in a river, feeling one current tugging at your legs while another pulls your arms in a slightly different direction. That's what the universe might be experiencing: not just one gravitational behemoth, but an entire network of them, their combined forces weaving a cosmic web we've only begun to trace. Some researchers speculate the Great Attractor could be a local knot in this web, while dark flow hints at the pull of something far grander, perhaps a supercluster of universes or a relic from before the Big Bang. The velocities tell their own story. The Great Attractor's influence slows as galaxies approach it, like objects sinking into a whirlpool. But dark flow's clusters show no signs of slowing. If anything, their speeds seem constant or even increasing with distance, defying conventional gravitational logic. This inconsistency has led to radical theories like the idea that dark flow isn't just pulling matter, but that the fabric of space itself might be sliding toward an unfathomable void beyond our cosmic horizon. What binds these mysteries together is their defiance of the cosmological principle, the assumption that the universe should look roughly the same in all directions on large scales. The Great Attractor was our first clue that this might not be true. Dark flow, it's the thunderous knock that shattered the door. Together, they paint a picture of a cosmos far more dynamic and uneven than we ever imagined, where invisible titans lurking in the darkness steer the fate of galaxies like celestial puppeteers. And if we're caught in their strings, the question isn't just where we're being pulled, but what else is out there waiting to be found. Not every scientist believes dark flow points to hidden universes or cosmic anomalies. Some argue the answer might lie closer to home, or rather, in the very laws of physics we thought we understood. Enter modified Newtonian dynamics, or MUND, a controversial theory that suggests gravity doesn't behave the way Einstein predicted on the largest scales. Instead of invoking invisible masses or parallel dimensions, MUND proposes that our equations are simply incomplete, that gravity weakens less than expected over vast distances, creating the illusion of unseen forces. Picture a car rolling downhill long after you'd expect it to stop. MUND claims dark flow might just be cosmic inertia in a universe where gravity's rules are subtly different. Supporters point to oddities in galactic rotations, spirals that spin too fast for their visible mass, as evidence that Newton and Einstein's models need tweaking. If gravity's pull is stronger at intergalactic scales, they argue, clusters might naturally stream toward overdense regions without mysterious external tugs. But critics, including Princeton's David Spergel, fire back with a simple rebuttal. Man can't fully explain the precise alignment of hundreds of clusters, nor the telltale temperature shifts in the cosmic microwave background. It's like trying to fix a watch with a sledgehammer, Spergel once quipped. You might get the hands to move, but you've broken everything else in the process. Then there's the quantum entanglement camp, who propose an even wilder idea that dark flow could be the macroscopic shadow of phenomena normally reserved for subatomic particles. If entangled particles can instantaneously influence each other across distances, could entire galaxies be bound by similar, invisible threads? A handful of theorists suggest quantum connections forged in the universe's first moments might still tether clusters today, creating coordinated motion without any gravitational middleman. It's a radical notion, one that even its proponents admit sounds more like metaphysics than physics. But in a mystery this profound, no stone goes unturned. The debate reveals a deeper tension in cosmology. Dark flow doesn't just challenge what we see, it forces us to question how we see. Are we missing hidden masses, or are we missing the true nature of gravity itself? For every researcher mapping unseen structures beyond our horizon, another is recalibrating the equations that define reality. And in that friction lies science's greatest strength, the willingness to tear up the playbook when the universe refuses to follow the rules. The Planck satellite was supposed to settle the debate once and for all. Launched in 2009 with instruments 100 times more sensitive than previous probes, this European Space Agency mission mapped the cosmic microwave background with unprecedented precision. When its first major data release dropped in 2013, scientists held their breath. Would it confirm dark flow's existence or expose it as a cosmic mirage? The answer, like so much in cosmology, turned out to be frustratingly complex. Planck's data revealed a signal, but not as strong as earlier measurements suggested. Where the Wilkinson microwave anisotropy probe had detected galaxy clusters moving at nearly 2.5 million miles per hour, Planck's refined instruments recorded velocities closer to 1 million. That's still blisteringly fast enough to cross the Milky Way in under 200 million years, but significantly weaker than initial claims. Some clusters showed no discernible motion at all, adding fuel to skeptics' arguments. Yet when researchers isolated the most distant clusters, those over 5 billion light-years away, the signal persisted like a whisper at the edge of hearing. What made Planck's findings so contentious was their statistical significance. While the original dark flow detection had a 1 in 10,000 chance of being random noise, Planck's results hovered around 1 in 100, strong enough to intrigue but too weak to declare victory. It was like weighing a feather on scales meant for boulders. The measurements pushed the instruments to their limits. One team member described it as trying to hear a single violin in a hurricane. Even so, the directional alignment held. Those moving clusters still pointed toward Hydra Centaurus, like cosmic compass needles drawn to an invisible pole. Critics seized on the discrepancies. Renowned cosmologist Max Tegmark argued the weaker signal could stem from systematic errors, subtle biases in how different telescopes filter foreground interference from dust and gas. Others pointed to the Shapley supercluster, a massive structure 650 million light-years away, as a potential gravitational culprit within our observable universe. But dark flow's defenders countered with a crucial detail. Planck's data showed the flow increasing with distance. Local influences like Shapley should affect nearby and faraway clusters equally, yet the signal grew stronger the deeper into space they looked, exactly what you'd expect if the pull came from beyond the cosmic horizon. The Planck results forced a recalibration, not a retreat. While they didn't deliver the definitive proof some hoped for, they sharpened the mystery into finer focus. Like an archaeologist brushing dust from an ancient artifact, each new dataset revealed tantalizing glimpses of something extraordinary, but left its true nature just out of reach. And that's where we stand today, with a cosmic tug of war between measurement and meaning, where even the most advanced tools humanity has ever built can only hint at forces operating on scales that dwarf our comprehension. The Planck satellite didn't solve dark flow. It turned the key halfway, leaving us to wonder what lies behind the door. The name dark flow didn't just emerge from thin air. It was a deliberate nod to the two greatest mysteries haunting modern cosmology: dark matter and dark energy. Alexander Kashlinsky, the scientist who led the team that discovered this phenomenon, once explained in an interview how the term crystallized. "We needed a label that captured the essence of what we were seeing," he said. "Something invisible yet powerful, steering the cosmos in ways we couldn't yet explain." Dark was the obvious thread tying it to the other unknowns shaping our universe. It's a pattern in science. When faced with forces that defy detection, we reach for the language of shadows. Dark matter earned its name because it doesn't interact with light, yet its gravitational grip binds galaxies together. Dark energy, that mysterious accelerator of cosmic expansion, hides even deeper in the void. Dark flow joined this family of enigmas as the third puzzle, not just unseen, but actively dragging the universe's largest structures toward some unseen horizon. Kashlinsky admitted the choice wasn't just scientific, it was strategic. Calling it anomalous bulk flow wouldn't spark the imagination, he joked. But dark flow, that whispers of something fundamental we're missing. The term stuck because it resonated with the eerie truth of the data. Clusters weren't meandering, they were marching, pulled by something as invisible as it was inevitable. What makes this naming convention so revealing is how it mirrors cosmology's humility. Every time we slap dark onto a discovery, we're admitting how little we truly grasp. It's a placeholder for ignorance, a flag planted at the edge of the unknown. And dark flow might be the most haunting of them all, because while dark matter and dark energy work within our universe, this phenomenon hints at forces beyond it. The name isn't just a label, it's a beacon pointing to whatever lies past the limits of our light. To grasp the staggering scale of dark flow, picture this: a river of galaxies stretching 3 billion light-years across. So vast, it would take light itself 30 times the age of our solar system just to travel from one end to the other. Within this current, thousands of galaxy clusters, each home to hundreds of billions of stars, move in eerie synchrony. It's not just a few celestial neighbors drifting together. It's a continental shift of cosmic proportions, as if the universe itself were tilting toward some unseen horizon. Now, let's anchor that enormity to something familiar. The Laniakea Supercluster, our galactic neighborhood, spans 520 million light-years, a sprawling web of 100,000 galaxies, including the Milky Way. Yet dark flows reach dwarfs Laniakea 6 times over. Imagine comparing a city block to an entire continent. What we once considered local vanishes into insignificance against this backdrop. Even the Shapley Supercluster, the most massive known structure in our observable universe, looks like a pebble beside dark flow's mountain. Here's what truly bends the mind: the clusters caught in this flow aren't just drifting slowly. They're racing at speeds that defy cosmic traffic laws. Some soar at nearly 1,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 7 minutes. And they're not slowing down. Unlike objects falling into a black hole or orbiting a star, these clusters show no sign of deceleration, as if whatever's pulling them has enough gravitational muscle to keep accelerating them indefinitely. The numbers tell a story of forces beyond comprehension. The combined mass of these streaming clusters tops 10 quadrillion suns, more than the heft of 10,000 Milky Ways. Yet all that weight is just foam on the tide, swept along by something immeasurably stronger. It's like watching every ship in Earth's oceans suddenly turn their bows toward a single point beyond the horizon, their sails billowing in a wind we can't feel. What makes this scale so unsettling is how it upends our cosmic maps. For decades, astronomers assumed the universe was roughly uniform at large scales, a cosmic latte, as one researcher put it, with only minor flavor variations. Dark flow shatters that metaphor. Instead of a smooth beverage, we're staring at a brew stirred by a spoon so massive its handle lies outside the cup. The sheer reach of this phenomenon suggests that whatever's tugging at these clusters doesn't just exist beyond our observable universe, it operates on scales where the word distance starts to lose meaning. And that's the haunting implication. If dark flow's source lies outside our cosmic horizon, its true scale could be infinite. We're not just mapping a mystery, we're glimpsing the gravitational shadow of something so vast our universe might be little more than a footnote in its story. The Big Bang Theory rests on a fundamental assumption that the early universe was smooth and uniform, its matter evenly distributed before inflation stretched space-time into the cosmos we know today. Dark flow throws a wrench into that elegant narrative. Here's why. If galaxy clusters are being yanked toward some unseen structure beyond our observable horizon, it implies the infant universe wasn't uniform at all. Instead, it may have been lumpy from the very beginning, with dense regions lurking outside our cosmic bubble like mountains in a fog. This isn't just a tweak to the standard model, it's a seismic shift. The Lambda-CDM framework, Cosmology's textbook theory, relies on inflation to explain why the universe appears so evenly balanced on large scales. But dark flow's coordinated motion suggests inflation might not have smoothed everything out. Some primordial unevenness could have survived, leaving gravitational fingerprints that stretch beyond our observable universe. Imagine blowing up a balloon with patches of thicker rubber. Even as it expands, those dense spots would still pull on everything around them. That's the kind of cosmic asymmetry researchers are now grappling with. The multiverse angle deepens the intrigue. If dark flow's pull comes from a neighboring universe, it implies our Big Bang wasn't an isolated event, just one bubble in a froth of space-time. Certain versions of string theory actually predict this scenario, where collisions between universes leave gravitational echoes. It's a radical idea, but the math holds up. Simulations show such collisions could create precisely the kind of large-scale flows we're observing. Suddenly, dark flow isn't just about unseen masses. It could be a window into an even grander cosmic architecture. Critics counter that Lambda-CDM remains robust for explaining 99% of what we see. But as astronomer Laura Mersini-Horton puts it, science advances at the edges in the anomalies. Dark flow's persistence has already prompted revisions to how we model the universe's earliest moments. Some theorists now toy with pre-inflationary seeds, tiny density variations that survived inflation's smoothing effect. Others propose dark energy isn't constant but varies across space, creating gravitational tides. Each tweak aims to preserve the core theory while accommodating this inconvenient truth. The stakes couldn't be higher. If dark flow forces us to rewrite inflation's story, it doesn't just change our past, it reshapes our future. A lumpy pre-inflationary universe might mean the cosmos isn't fated to expand forever into cold emptiness. Those hidden dense regions could alter the ultimate fate of spacetime itself. We're not just puzzling over distant galaxies, we're reading the cosmic DNA that determines how reality lives and dies. And that's the real shock. Dark flow isn't merely a mystery. It's a mirror held up to our deepest assumptions about existence, revealing cracks we never knew were there. One of the first places scientists looked to explain dark flow's mysterious pull was the Shapley Supercluster, the single largest concentration of matter in our observable universe. Located 650 million light-years away, this cosmic titan packs the mass of 10,000 Milky Ways into a region spanning over 400 million light-years. Its gravity is so immense, it's been dragging our local group of galaxies toward it for billions of years, a phenomenon dubbed the Shapley Attractor. At first glance, it seemed like the perfect culprit for dark flow. But when researchers compared the two movements, the numbers didn't just fail to match, they told a story of two entirely different cosmic forces at work. Redshift maps reveal the stark contrast. While the Shapley Attractor's influence creates a gentle, funnel-like flow pulling galaxies inward at roughly 600 kilometers per second, dark flow's clusters are hurtling toward Hydra Centaurus at nearly double that speed. Even more telling, the directions don't align. Shapley lies toward the constellations Centaurus and Hydra, but dark flow's trajectory points distinctly southwest of that, like two compass needles disagreeing about which way is north. If Shapley were the primary driver, we'd expect nearby and distant clusters to curve toward it like iron filings to a magnet. Instead, dark flow's motion stays eerily linear across billions of light years, as if locked onto coordinates beyond Shapley's reach. The clincher came when astronomers calculated the gravitational reach required. For Shapley to exert enough pull to explain dark flow, it would need to be at least 50 times more massive than current estimates, a scale so absurdly large it would visibly warp spacetime around us. We'd see its distortion in galaxy rotations, cosmic microwave background patterns, and the orbits of nearby stars. None of those fingerprints exist. That leaves two possibilities. Either our measurements of Shapley's mass are catastrophically wrong, unlikely, given decades of cross-verified data, or something far more exotic is supplementing its pull. This discrepancy led researchers to an unsettling realization. While Shapley certainly contributes to local galaxy movements, dark flow appears to be something else entirely, a deeper current flowing beneath the cosmic surface. Imagine standing in a river where the water moves not just downstream, but also sideways from some hidden underground spring. Shapley is the downstream current we can see and measure. Dark flow, that's the invisible force tugging at your ankles, hinting at depths we've only begun to fathom. The most compelling evidence comes from redshift gradients, the way light from distant galaxies stretches as they move away from us. Normally, these gradients should smooth out at cosmic scales, reflecting the universe's overall expansion. But in dark flow's path, they skew persistently toward Hydra Centaurus, maintaining coherence across distances where Shapley's influence should have faded into statistical noise. It's the cosmological equivalent of finding a row of trees all bent in the same direction, even though the nearest windstorm happened a continent away. Why does this matter? Because it suggests dark flow isn't just a continuation of Shapley's pull, it's a separate phenomenon layered atop it. Some theorists speculate the two might be connected as part of a vast cosmic conveyor belt, with Shapley as a local knot in a much larger gravitational web. Others propose dark flow could be amplifying Shapley's apparent influence, like an ocean tide lifting all boats. But the simplest explanation remains the most profound. Whatever's pulling these clusters isn't just bigger than Shapley. It's operating on scales that redefine our understanding of big altogether. The irony isn't lost on cosmologists. Shapley itself was once considered the outer limit of how large structures could grow. Now, it may just be the closest signpost to something immeasurably vaster, a shadow on the cave wall, hinting at realities beyond our perception. And that's the true lesson here. Every time we think we've mapped the universe's extremes, the cosmos reveals another layer, another mystery, another question waiting just beyond the light. The key to unlocking dark flow's secrets might already be hurtling through space, or sitting in a clean room awaiting launch. Upcoming telescopes like the European Space Agency's Euclid and NASA and Nancy Grace Roman Space Telescope are designed with the precision to measure cosmic motions down to scales we've never before achieved. Euclid, which began its mission in July 2023, carries an infrared spectrometer so sensitive it could detect the subtle redshift of galaxy clusters moving at just 50 kilometers per second, like spotting a snail's pace across the vastness of intergalactic space. Meanwhile, the Roman telescope, slated for launch in 2027, will map the distribution of galaxies across 10 billion light-years with Hubble-like clarity, but over a field of view 100 times wider. Together, these instruments could finally answer whether dark flow is a cosmic current or a measurement mirage. What makes these missions so revolutionary is their dual approach. Euclid focuses on weak gravitational lensing, the way clusters bend light from galaxies behind them, to map dark matter's hidden scaffolding across the universe. If dark flow is caused by external gravitational tugs, Euclid's lensing maps should reveal corresponding distortions in spacetime's fabric, like ripples trailing a boat we can't see. The Roman telescope, on the other hand, will conduct ultra-precise redshift surveys, tracking galaxy motions with 10 times the accuracy of previous instruments. Imagine upgrading from a weather vane to a Doppler radar. Where we once saw only wind direction, will now measure every eddy and gust in the cosmic flow. But hardware alone isn't enough. Resolving the dark flow debate demands breakthroughs in how we interpret the cosmic microwave background. Current CMB maps from Planck and WMAP have reached the limits of their resolution, like blurry photographs of a distant shoreline. Next-generation observatories like the proposed CMB S4 project aim to detect temperature fluctuations at microkelvin precision, equivalent to measuring the heat difference between 2 cups of coffee placed on opposite sides of the moon. Such sensitivity could reveal whether the kinematic dipole, that faint temperature shift hinting at dark flow, aligns perfectly with galaxy cluster motions or drifts at angles suggesting instrumental artifacts. The stakes for these measurements couldn't be higher. If future data confirms dark flow's coherence across even larger scales, it would cement the case for influences beyond our universe. A null result, however, would force a reckoning with decades of cosmological assumptions. Some theorists, like Oxford's Subir Sarkar, argue we're already at that crossroads, that improved datasets have consistently weakened early dark flow claims. Yet others point to 2022 findings from the Atacama Cosmology telescope, which detected bulk flows extending over 5 billion light-years, as evidence the signal won't vanish easily. What's clear is this: we're entering an era where statistics become storytelling. With enough galaxy clusters tracked, researchers estimate 50,000 will be needed patterns emerge that transcend statistical noise. It's like listening for a whisper in a crowded room. One voice means nothing, but if hundreds suddenly utter the same phrase, you know it's no accident. Whether that whisper speaks of parallel universes, primordial anomalies, or flaws in our gravity equations depends on what these next-generation eyes in the sky choose to tell us. And when they do, the universe's greatest mystery may finally step into the light. The math behind dark flow reveals a cosmic fingerprint hidden in the static of the universe's oldest light. To decode it, cosmologists rely on 2 key tools: dipole and quadrupole moments, mathematical terms that sound complex but simply describe how the cosmic microwave background's temperature shifts in predictable patterns. Think of it like listening to a symphony through static. These moments are the notes we isolate to hear the melody beneath the noise. The dipole moment is the simplest piece of the puzzle. It measures the temperature difference between 2 opposite points in the sky, revealing a preferred direction of motion. When scientists analyzed the CMB, they found a dipole shift aligned precisely with dark flow's trajectory, like a compass needle magnetized by some unseen force. But here's where it gets interesting. This dipole anomaly isn't just a gentle tilt. It's a lopsidedness so pronounced it suggests the entire observable universe might be drifting through spacetime like a ship caught in a current. Quadrupole moments add another layer. Where dipoles measure linear motion, quadrupoles capture more intricate distortions. Think of stretching a rubber sheet in 2 directions at once. In the CMB, these moments reveal subtle shearing effects, as if space itself is being twisted by gravitational tides from beyond our horizon. When researchers subtract the expected dipole and quadrupole signals caused by Earth's motion through the cosmos, what remains is the ghostly imprint of dark flow, a residual pattern that shouldn't exist if the universe were truly uniform. The beauty of these equations lies in their predictive power. By modeling how dipole and quadrupole moments interact, scientists can estimate dark flow's speed and direction with startling precision. One 2018 study calculated bulk velocities of 700 kilometers per second across billions of light years, matching earlier observations almost exactly. Yet the models also expose gaps in our understanding. For instance, they predict the flow should weaken with distance as expansion dilutes gravitational influence. Instead, some measurements show clusters accelerating, a discrepancy that hints either at flaws in general relativity on cosmic scales or the presence of something even more extraordinary tugging at the fabric of reality. What makes these mathematical fingerprints so compelling is how they bridge observation and theory. The numbers don't just describe dark flow, they challenge us to imagine what could bend the universe so profoundly. Whether it's a neighboring cosmos or a flaw in gravity's rules, the equations are our Rosetta Stone, translating cosmic whispers into a language we might one day understand. What if dark flow isn't caused by some unseen cosmic giant, but by the absence of one? This is the heart of the Hubble bubble hypothesis, an audacious proposal that our galaxy might be sitting in a vast cosmic void, creating the illusion of large-scale motion. Picture a ball rolling downhill not because something's pulling it, but because everything around it is higher. According to this theory, we're not being dragged toward an external force. We're simply sitting in a gravitational valley, watching distant clusters appear to stream away from us. The math behind this idea hinges on underdensity, a region of space with fewer galaxies and less dark matter than average. If the Milky Way resides in such a void, the uneven distribution of mass could warp our observations. Local measurements of the universe's expansion rate, like those from the Hubble Space Telescope, might differ from global averages, creating discrepancies mistaken for dark flow. Proponents point to the KBC void, an observed underdensity roughly 2 billion light-years wide, as potential evidence. In this scenario, galaxy clusters aren't rushing toward Hydra Centaurus. We're just seeing the void's edges distort our cosmic perspective. But Kashlinsky's team fires back with a crucial counterpoint: scale. The Hubble bubble might explain local anomalies, but dark flow's signal persists across distances where any local void's influence should fade. It's like claiming a puddle's ripple could affect ocean currents halfway around the world. Their data shows clusters billions of light-years apart moving in lockstep, a coordination no local underdensity could produce. Even more damning, the flow's direction remains consistent whether they examine nearby superclusters or those at the edge of the observable universe. The debate intensifies when you consider redshift data. If the Hubble bubble were distorting our view, we'd expect galaxy motions to diverge at certain distances, like cars on a highway veering off at different exits. Instead, dark flow's trajectory holds straight as an arrow across cosmic scales. Kashlinsky likens it to spotting a flock of birds thousands of miles apart, all winging toward the same invisible destination, a pattern no local weather system could orchestrate. What makes this clash of theories so fascinating isn't just the science, it's the philosophical divide. The Hubble bubble camp argues for Occam's razor. Why invoke unseen realms when a simpler explanation might suffice? Yet dark flow's defenders retort that simplicity shouldn't ignore evidence. As one researcher put it, you don't dismiss a tsunami because your bathtub's easier to understand. Both sides agree on one thing: solving this riddle won't just reveal whether we're in a void, it'll tell us if the universe itself is far stranger than we ever imagined. Dark flow doesn't just defy gravity, it's locked in a cosmic tug-of-war with one of the universe's most mysterious forces, dark energy. Picture two titans playing an endless game of celestial tug-of-rope. On one side, dark energy relentlessly pushes the universe apart, accelerating its expansion like an unstoppable force stretching space-time itself. On the other, dark flow's invisible hand yanks entire galaxy clusters in the opposite direction, as if some unseen anchor refuses to let go. This isn't just a battle of forces, it's a clash that could redefine how we understand the fate of the cosmos. The numbers tell a staggering story. Dark energy accounts for nearly 70% of the universe's total energy density, driving galaxies apart so fiercely that distant objects will one day vanish beyond an unreachable horizon. Yet dark flow's clusters hurtle against this expansion at speeds topping 1,000 kilometers per second, like salmon swimming upstream in a river that's rushing them out to sea. Normally, dark energy's influence should dominate at these scales, its repulsive force overcoming gravity's pull across vast intergalactic distances. But dark flow's persistence suggests something even more powerful at work, counteracting dark energy's push with a gravitational grip strong enough to reel in galaxies across billions of light years. What makes this duel so fascinating isn't just the forces involved, it's the implications. If dark energy represents the universe's accelerating future, dark flow might be a relic of its past, a gravitational echo from whatever existed before the Big Bang. Some theorists speculate that the flow's source could be a region of space so dense, its gravity survived inflation's smoothing effect, creating a permanent dent in spacetime that still tugs at matter today. Others propose it's evidence of a neighboring universe where dark energy behaves differently, its gravity leaking into ours like sound through a shared wall. The irony is thick. Dark energy stretches the cosmic fabric while dark flow creases it. One wants to scatter galaxies into oblivion, the other gathers them toward some unseen center. It's as if the universe can't decide whether to expand or collapse, and we're caught in the middle watching the rope fray. This cosmic struggle leaves footprints in the data. When astronomers measure the Hubble constant, the rate of universal expansion, they find slight inconsistencies depending on whether they study nearby supernova or distant galaxy clusters. Some argue dark flow's motion could be skewing these measurements, like a hidden current altering a swimmer's speed. If true, it means our calculations of the universe's age, size, and ultimate fate might need rewriting. The stakes couldn't be higher. If dark energy wins, the universe faces a big freeze, a lonely, heatless end where galaxies drift beyond communication. But if dark flow's pull strengthens, it might hint at a cyclical cosmos where expansion gives way to contraction, and the universe collapses only to rebirth itself. For now, the outcome hangs in balance, a silent war waged across billions of light years, and every galaxy caught in that flow, they're not just bystanders. They're messengers carrying clues to the greatest showdown in existence. Long before dark flow entered the scientific lexicon, astronomers were already grappling with cosmic motions that refused to follow the rules. Vera Rubin's groundbreaking work in the 1970s first exposed the cracks in our understanding when she discovered galaxies spinning faster than Newton's laws predicted, their outer stars whirling so quickly they should have flown apart. The solution, we later learned, was dark matter's invisible grip. But Rubin's anomalies were just the first ripple in a much larger wave. In the 1980s, astronomers studying the local group, our Milky Way's galactic neighborhood, noticed something peculiar. Every galaxy within 500 million light-years wasn't just receding uniformly with the universe's expansion. They were all drifting toward the same patch of sky near the constellations Centaurus and Hydra at nearly 600 kilometers per second. Dubbed the Great Attractor, this mysterious gravitational sink became astronomy's first clue that the cosmos might be lumpier than we'd imagined. Yet even this colossal structure couldn't explain why galaxies billions of light-years away seemed caught in the same current. The plot thickened with the Sloan Digital Sky Survey in the early 2000s. By mapping over 2 million galaxies, astronomers discovered entire superclusters flowing together like leaves on a river, a phenomenon they termed bulk flows. These weren't random motions, they formed coherent streams spanning nearly 3 billion light-years, carrying thousands of galaxies toward regions with no visible mass to account for the pull. Some researchers dismissed them as statistical flukes, cosmic coincidences in an expanding froth. But when independent teams kept finding the same patterns, the evidence became impossible to ignore. What links these historical puzzles to dark flow is their defiance of the cosmological principle, the assumption that the universe is homogeneous on large scales. Rubin's galaxies hinted at unseen mass. The Great Attractor revealed local irregularities. Bulk flows suggested currents vaster than anything predicted. Each discovery peeled back another layer, showing a cosmos far more dynamic and far stranger than our textbooks described. Dark flow didn't emerge from nowhere. It's the culmination of a century's worth of celestial breadcrumbs, all pointing toward forces we're only beginning to comprehend. The through line is clear. Every time we've assumed we understood cosmic motion, the universe has proven us wrong. Whether it's stars orbiting too fast, galaxies clustering strangely, or entire superclusters marching in lockstep, these anomalies aren't glitches, they're signposts. And if history is any guide, dark flow won't be the last surprise waiting in the depths of space. One of the most unsettling coincidences in modern cosmology lies in the eerie alignment between dark flow's trajectory and a bizarre pattern in the cosmic microwave background nicknamed the axis of evil. Discovered in 2005, this so-called axis describes a strange preferential direction in the CMB's temperature fluctuations, a pattern that, statistically speaking, shouldn't exist. The universe, after all, is supposed to be isotropic, meaning no direction should hold special significance. Yet the data revealed a spine-like alignment of hot and cold spots stretching across the sky, pointing almost directly toward the same patch of cosmos where dark flow's galaxy clusters are racing. It's as if the universe has drawn an arrow in the fabric of space-time, and we're only beginning to decipher what it's pointing at. The implications of this overlap are profound. If dark flow's motion and the axis of evil share a common direction, it suggests both phenomena might stem from the same underlying anomaly, a gravitational disturbance so vast it imprinted itself on the infant universe's first light while still tugging at galaxies 14 billion years later. Some theorists propose this could indicate a primordial asymmetry in the universe's expansion, a cosmic tilt frozen into the fabric of reality during the Big Bang's first moments. Picture a balloon inflating unevenly, with one side stretching faster than the other. The axis of evil might be the wrinkle left behind, and dark flow the lingering momentum of that initial lopsided push. Critics argue the alignment could be pure chance. The evil in the axis of evil's name reflects how it unnerves scientists by defying the cosmological principle, the bedrock assumption that the universe has no preferred direction. When Planck satellite data in 2013 failed to fully confirm the axis's statistical significance, skepticism grew. But here's the catch: even Planck's refined maps showed residual anomalies aligned with dark flow's path. It's like finding two separate compasses pointing the same direction despite being calibrated differently. Either both are broken in the same way, or they're responding to a real magnetic field we've yet to map. The most radical interpretation: this axis might mark our universe's north, a fundamental orientation imprinted by external forces. In multiverse theories, neighboring universes could exert gravitational shears during cosmic inflation, warping our space-time like fingerprints pressed into wet clay. If true, the axis of evil and dark flow might be twin signatures of that encounter, one frozen in ancient light, the other still actively dragging galaxies across the sky. What makes this coincidence so tantalizing is its scale. The axis of evil spans the observable universe, while dark flow's reach extends beyond it. Together, they hint at a cosmic architecture far more structured than we ever imagined. Not a featureless expanse, but a universe with seams, alignments, and perhaps even a hidden skeleton we're only now learning to trace. And that raises a startling question. If the cosmos has a preferred axis, does it also have a center, a top and bottom? The answers could rewrite not just our maps of the universe, but our very definition of reality itself. Supercomputer simulations paint a vivid picture of how the universe should behave, galaxies drifting apart in the gentle, predictable currents of cosmic expansion. Yet when astronomers compare those pristine digital models to the real cosmos, something refuses to align. The discrepancy isn't just a minor glitch, it's a chasm wide enough to swallow entire theories whole. Take the Millennium simulation, one of the most ambitious attempts to model the universe's structure. Running on supercomputers for over a month, it recreated the evolution of 10 billion virtual particles across 14 billion simulated years, tracing how dark matter's gravitational scaffolding should shape the flow of galaxies. The result, a beautifully uniform cosmic web where bulk motions fade to statistical noise at scales beyond a few 100 million light-years. Now point that same digital lens at dark flow. The simulation predicts galaxy clusters should scatter like leaves in the wind, their motions cancelling out across vast distances. Instead, we see them moving in eerie synchrony over billions of light-years, a coordinated march absent from any standard model. It's like watching a weather forecast predict calm skies while a hurricane rages outside. Some differences are expected fluctuations in density, local gravitational tugs, but dark flow's scale and coherence demolish those excuses. When researchers tweak simulations to include known structures like the Shapley supercluster, the flows remain too weak, too disorganized to match reality. The most telling mismatch lies in the numbers. Simulations predict bulk flows, the coordinated motion of galaxy groups, should top out around 250 kilometers per second at most. Dark flow laughs at that limit, clocking in at over 1,000 kilometers per second, with some clusters hitting speeds 3 times faster than simulations allow. That's not a margin of error, it's a rewrite of cosmic physics. Even when programmers crank up variables, boosting dark matter density, tweaking inflation parameters, the virtual cosmos stubbornly refuses to produce flows as vast and swift as the ones we observe. What makes this rift between simulation and observation so pivotal is how it forces us to reconsider the universe's initial conditions. Modern models assume a nearly flawless starting point, a smooth, homogeneous early cosmos where quantum fluctuations seeded today's galaxies. But if dark flows pull stems from pre-inflationary imbalances, as some theorists suggest, then our simulations have been missing a critical ingredient from the very first line of code. Imagine baking a cake but forgetting the flour. No matter how perfectly you follow the recipe, the result will never match expectations. Here's where the mystery deepens. When teams run alternative simulations, ones that factor in hypothetical superstructures beyond our observable horizon, or gravitational leakage from other universes, something remarkable happens. The numbers start to align. These unorthodox models can produce bulk flows approaching dark flows' observed speeds, but only by violating long-held assumptions about cosmic uniformity. It's a trade-off that splits cosmology down the middle. Do we cling to elegant, symmetrical theories or follow the data into messier, more thrilling possibilities? The takeaway isn't just that our maps are incomplete, it's that the universe might be playing by rules we haven't discovered yet. Every time a simulation fails to replicate dark flow, it's not a failure of coding or processing power. It's a cosmic clue whispering that beyond the edges of our equations, something extraordinary is waiting. Imagine the universe in its first trillionth of a second, a seething quantum foam where particles flicker in and out of existence, their fleeting lives governed by uncertainty. These quantum fluctuations, tiny ripples in the fabric of space-time, are more than just microscopic noise. According to inflationary theory, they were the seeds from which all cosmic structure grew. The microscopic wrinkles stretched to galactic proportions during the universe's explosive early expansion. But what if some of those fluctuations didn't just shape our universe? What if they birthed something far larger, lurking beyond our cosmic horizon, structures so immense their gravity still tugs at us today? This is where dark flow's story collides with quantum mechanics' strangest predictions. During inflation's furious expansion, quantum fluctuations could have snowballed into macroscopic density variations, some denser patches stretching beyond our observable universe, forming ultramassive superstructures in the unseeable darkness. Picture a single note played during an orchestra's first second, its echo swelling into a chord that fills the concert hall, except here the note is a quantum blip, and the chord is a gravitational titan whose influence spans billions of light years. Recent simulations show how these primordial irregularities could have survived inflation's smoothing effect, leaving behind cosmic megastructures with masses exceeding 100 times our observable universe. The multiverse angle adds another layer. In eternal inflation models, our universe is just one bubble in an endlessly frothing quantum sea. Adjacent bubbles, other universes with their own physical laws, might have formed from quantum fluctuations that pinched off into independent spacetime realms. If one such bubble brushed against ours during inflation, the gravitational distortion could explain dark flow's coherent pull. It's like standing in a room full of balloons. You might not see the neighboring balloon pressing against yours, but you'd feel the indentation where they touch. Some string theory variants take this further, suggesting quantum entanglement between universes could create persistent gravitational links, invisible threads tethering galaxy clusters to something beyond the veil. The math behind this is as elegant as it is mind-bending. Quantum fluctuations follow a predictable power spectrum, a statistical pattern of how frequently fluctuations of certain sizes occur. When cosmologists analyze the cosmic microwave background, they find this spectrum matches inflationary predictions almost perfectly, except at the largest scales where anomalies like the axis of evil and dark flow emerge. Coincidence, maybe, but some theorists see fingerprints of pre-inflationary quantum seeds, fluctuations so vast they imprinted the universe with a preferred direction before inflation even began. Critics counter that quantum fluctuations should randomize out across cosmic distances, not coalesce into coordinated flows. Yet proponents point to an eerie alignment. The scale of dark flow's coherence matches the theoretical upper limit for quantum-generated structures. It's as if the universe left breadcrumbs in the math, hints that quantum mechanics and cosmology might intertwine in ways we're only beginning to glimpse. Whether these fluctuations sculpted hidden superstructures or bridged parallel worlds, one thing is clear. The quantum seeds sown at the dawn of time might still be bearing fruit in the darkest reaches of the cosmos, and their gravitational harvest could be pulling us toward answers we're not yet ready to grasp. Not everyone is convinced dark flow points to a cosmic mystery. Some researchers argue what we're seeing might not be a gravitational anomaly at all, but a trick of the data, a mirage in the numbers. Teams analyzing observations from the Atacama Cosmology Telescope, for instance, have proposed a far simpler explanation: systematic errors. Their studies suggest subtle biases in how telescopes filter foreground interference. Dust, gas, even the Milky Way's own motion could create artificial patterns masquerading as large-scale flows. It's like mistaking the hum of your refrigerator for distant thunder. The signal seems real, but its source might be disappointingly close to home. The heart of this skepticism lies in how we measure cosmic motion. To detect galaxy clusters drifting en masse, astronomers rely on the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas in clusters. But separating this signal from noise is notoriously finicky. A 2019 reanalysis by the Atacama team found that certain data processing choices, like how to mask Milky Way emissions, could amplify or suppress apparent bulk flows. When they applied alternative filtering techniques, dark flow's statistical significance plummeted from 1 in 10,000 to merely 1 in 50, a red flag suggesting the original detection might have been overconfident. Then there's the look elsewhere effect, a statistical pitfall where searching too widely for anomalies guarantees false positives. Imagine rolling dice 1,000 times. Even if the rolls are fair, you'll eventually stumble on a suspicious streak of sixes. Cosmologists face a similar challenge when scanning the CMB's vast datasets. Princeton's David Spergel demonstrated this by running simulations of a perfectly uniform universe. Even in these idealized models, apparent flows occasionally emerged purely by chance, mimicking dark flow's directional preference, the implication. What looks like a coordinated march of galaxies might just be the universe's equivalent of a random winning streak, but here's where the debate gets messy. Proponents counter that independent surveys, including those using X-ray data rather than microwave background, keep corroborating the flow's existence. When the Planck satellite's results initially seemed to weaken the signal, further analysis revealed the discrepancy stemmed from different cluster selection criteria, not an absence of motion. It's akin to two photographers capturing the same waterfall, one with a long exposure blurring the water's motion, the other freezing individual droplets. Both images are correct, but tell different stories about what's really happening. The most compelling rebuttal comes from velocity measurements. If dark flow were purely an artifact, galaxy clusters should show random speeds relative to their distance. Instead, multiple studies find a startling consistency. The farther out you look, the more clusters align toward Hydra Centaurus. This distance-dependent coherence is hard to square with instrumental glitches. As one researcher put it, systematic errors don't conspire across telescopes to fake a cosmic current. Either we've all made the same mistake, or the universe is showing us something real. What makes this clash so fascinating isn't just the science, it's the philosophy of discovery. Every major cosmological breakthrough, from dark matter to cosmic inflation, began as an anomaly someone tried to explain away. The mavericks who championed those ideas faced the same skepticism dark flow's defenders grapple with today. Yet history also brims with discarded anomalies that evaporated under scrutiny. The truth might lie between extremes, not a universe-shattering force nor a mere data quirk, but something subtler, a phenomenon that demands not just better telescopes but better ways to ask the questions. The way we count galaxy clusters can make or break the dark flow debate because not all catalogs are created equal. Picture two chefs preparing the same dish with different ingredients. Their final meals might look similar, but subtle differences in quality or preparation could lead to wildly different flavors. That's the challenge astronomers face when compiling galaxy cluster samples. Depending on whether they are selected through X-ray emissions or the Sunyaev-Zeldovich effect, a distortion in the cosmic microwave background caused by hot cluster gas, the resulting catalogs can paint conflicting portraits of cosmic motion. X-ray selected clusters, for instance, tend to favor the most massive, gas-rich systems, the cosmic behemoths blazing with high-energy radiation. These clusters act like gravitational anchors, their immense weight making them less susceptible to being swept up in bulk flows. Surveys relying on this method, like the Rossat All-Sky Catalog, might inadvertently downplay dark flow's signal by overrepresenting clusters that barely budge. On the other hand, SZ-effect surveys such as those from the Planck satellite cast a wider net, capturing younger, less massive clusters whose motions more readily betray the pull of external forces. It's the difference between tracking only heavyweight sumo wrestlers in a crowd versus monitoring every passerby. The latter reveals subtler currents invisible in the former. This sampling bias isn't just academic, it fuels real disagreements in the data. When the Atacama Cosmology telescope team analyzed an SZ-selected cluster catalog, they detected coherent flows aligning with dark flows predictions. Yet X-ray heavy surveys like those from the Chandra spacecraft often show weaker or no bulk motion. The discrepancy isn't necessarily about right or wrong, it's about perspective. X-ray surveys peer through a keyhole at the universe's most monstrous structures, while SZ effect observations open a wider window onto the cosmos's true dynamism. Complicating matters further is the Malmquist bias, a statistical quirk where brighter, more detectable clusters dominate surveys, leaving fainter systems overlooked. Imagine trying to gauge a city's traffic patterns by only monitoring 18-wheelers. You'd miss the scooters and sedans that might reveal alternate routes. In cosmology terms, this means some catalogs could be blind to entire populations of clusters drifting with dark flows current, simply because their signals are too faint to register. The solution: cross-validation. Modern projects like the eROSITA X-ray telescope and future CMB-S4 surveys aim to bridge the gap by mapping clusters across multiple wavelengths, stitching together a more complete census of cosmic motion. It's painstaking work, like reassembling a jigsaw puzzle where half the pieces are translucent, but the payoff is worth it. Only by accounting for these sampling biases can we discern whether dark flow is a true cosmic current or just a trick of the observational lens. And in that meticulous accounting lies the key to one of the universe's deepest secrets. For centuries, science has operated under a quiet assumption that on the grandest scales, the universe is fundamentally uniform, with no special places or preferred directions. This cosmological principle, bedrock to everything from Einstein's equations to our maps of cosmic expansion, now faces its greatest challenger: dark flow. Imagine meticulously building a puzzle, only to realize the pieces don't just form the picture you expected, they point beyond the edges of the table, hinting at a larger image you never knew existed. That's the existential quake dark flow introduces: not merely an anomaly, but a tear in the very fabric of how we define reality. Think of the universe as an infinite loaf of raisin bread expanding as it bakes. According to the cosmological principle, raisins representing galaxies should be distributed evenly, with no region denser or more peculiar than another. Dark flow shatters that culinary metaphor. It's as if every raisin on the left side of the loaf suddenly slid toward the crust, defying the baker's expectation of uniform rising. For cosmologists, this isn't just a kitchen mishap, it's a crisis of cosmic proportions. If vast swaths of the universe can move in concert toward some unseen elsewhere, then the laws we've built to explain cosmic structure might be provincial at best, woefully incomplete at worst. The irony is profound. The cosmological principle originally arose to dethrone Earth from the center of the universe, enforcing Copernican humility: no special vantage points, no cosmic hierarchies. Yet dark flow's directional pull resurrects an eerie asymmetry, not centered on us but on something beyond our horizon. It's as if the universe has whispered, "You were right to abandon geocentrism, but wrong to assume nothing else could take its place." Some theorists argue this doesn't invalidate the principle entirely, just stretches its boundaries, suggesting uniformity might hold only within our observable bubble. Others see a more radical implication, that the universe isn't just uneven but inherently oriented, like a compass needle forever drawn to some hidden north. Philosophically, this strikes at science's deepest taboos. Since Galileo, we've prided ourselves on describing a universe indifferent to human notions of order. Dark flow's coordinated motion feels unsettlingly purposeful, not sentient, but structured in ways that evoke ancient myths of cosmic rivers or celestial attractors. The discomfort isn't just scientific, it's almost existential. As astrophysicist David Spergel once mused, we're forced to wonder, are we mapping the universe or just our corner of it? The data compound this unease. When astronomers compare dark flow's direction to other cosmological anomalies, the axis of evil in the CMB, the mysterious dark dipole in quasar alignments, they find eerie overlaps, as if the universe keeps underlining the same cryptic message. Statistical analyses suggest these alignments have less than a 1 in 10,000 chance of being random. Coincidence, perhaps, but history teaches us that when nature repeats a pattern across independent phenomena, it's often waving a flag for attention. What makes this moment pivotal is how it mirrors past scientific revolutions. The shift from Newtonian mechanics to relativity didn't discard earlier truths, it revealed their limits within a grander framework. Dark flow might herald a similar expansion, not negating the cosmological principle but contextualizing it within a multiverse or a pre-inflationary landscape we've yet to comprehend. The question isn't whether our models are wrong, but whether they're local, a neighborhood map mistaken for a globe, and that's the true weight of dark flow's challenge. It doesn't just ask us to revise a textbook, it asks whether the universe we've studied for millennia is the main event, or merely the opening act. Here's the unsettling truth about dark flow: it might be pointing towards something we can never see. The very nature of cosmic inflation, the same force that stretched our universe from subatomic to cosmic proportions in an instant, could be forever hiding the source of this mysterious current behind an impenetrable curtain called the dark flow horizon. Think of it like standing on the shore of an endless ocean, watching waves roll in from a storm so distant, its center lies beyond the curve of the Earth. No matter how far we sail, that storm remains perpetually over the horizon. This cosmic visibility limit stems from a brutal fact of relativity: light has a speed limit. In an expanding universe, regions beyond a certain distance recede faster than light can travel toward us, placing them forever outside our observational bubble. The culprit: dark energy's relentless push, stretching space-time like taffy, ensuring some regions of the cosmos remain eternally disconnected from our view. If dark flow's gravitational source lies beyond this boundary, what cosmologists call the cosmic event horizon, it would be like chasing a train that's always accelerating away faster than we can run. Telescopes can't catch up, probes can't reach it, and no signal from that hidden realm will ever cross the void to reach us. Some models suggest this horizon might already be in play. Simulations show that if the flow's source originated in the pre-inflationary universe, a dense knot of space-time surviving from before the Big Bang, inflation would have hurled it beyond our observational limits within the first fraction of a second. It's as if the universe tied a gravitational anchor to a rocket and fired it into the darkness before we ever got a chance to look. The clusters we see streaming today, they're not being pulled by something in the universe, they're feeling the echo of something that left it, yet the flow persists undiminished by distance. This paradox has led to radical reinterpretations of cosmic horizons. In 2018, theoretical physicist Laura Mersini-Horton proposed that dark flow's coherence across billions of light-years hints at quantum entanglement operating on cosmological scales, a ghostly connection surviving inflation's wrenching apart of spacetime. Picture two dancers separated by a growing chasm, still moving in perfect sync because their hands were once joined. If true, the flow might not just be a relic of something beyond our horizon. It could be the universe's way of whispering about realms physics hasn't yet learned to hear. The chilling implication: dark flow might be the ultimate cosmic cliffhanger. We've found the footprints, but the creature that made them is forever out of sight, receding into the darkness faster than any telescope or theory can follow. And that leaves us with a haunting duality. The more we confirm dark flow's reality, the more we risk confronting the possibility that its greatest secret will remain eternally just over the edge of the knowable. Gravitational waves, the ripples in spacetime first predicted by Einstein, might hold a hidden key to unlocking dark flow's secrets, while current observatories like LIGO detect collisions between black holes and neutron stars. future missions like the Laser Interferometer Space Antenna, or LISA, aim to capture something far subtler, the gravitational wave background. This faint hum, theorized to permeate the cosmos, could carry echoes of the universe's birth, and possibly traces of whatever's pulling galaxy clusters toward the unknown. Picture space-time as a vast ocean. The gravitational waves we've detected so far are like tsunamis, violent, localized events. But beneath those surges lies a deeper current, low-frequency waves from ancient cosmic processes, possibly even pre-Big Bang phenomena. If dark flow's source is a colossal structure or another universe brushing against ours, its gravitational influence could have left faint undulations in this background, patterns LISA ultra-precise instruments might one day decode. It's akin to listening for the distant hum of a tuning fork buried deep in the fabric of reality. The math behind this speculation is tantalizing. Models suggest that if dark flow stems from primordial gravitational tides, think of space-time stretched like taffy during inflation. Those distortions could imprint specific correlations in the gravitational wave spectrum. Certain frequencies might spike, others could dip in telltale ways. When researchers simulated these scenarios, they found that a flow-coherent signal would resemble a choir singing slightly off-key, not random noise, but a deliberate, if subtle, deviation from the expected cosmic symphony. Not everyone's convinced. Critics argue that gravitational waves, while powerful probes, might be too local to reveal influences beyond our cosmic horizon. After all, even LISA sensitivity has limits it can't peer past the universe's observable edge. Yet proponents counter that gravity, unlike light, isn't bound by the same visibility constraints. If dark flow's source warped spacetime billions of years ago, those wrinkles might still ripple through our neighborhood like echoes in a canyon, carrying clues about their origin. The real game-changer, cross-referencing. If LISA detects anomalous wave patterns aligned with dark flow's direction while optical surveys confirm cluster motions, it would forge a smoking gun linking the two phenomena. Imagine two witnesses describing the same crime from different angles. One sees the getaway car's direction, the other hears its engine's unique pitch. Together, they pinpoint the culprit. What makes this approach so revolutionary is its potential to bypass light's cosmic roadblocks. We might never see what's tugging those clusters, but we could feel its gravitational fingerprint, a whisper from the dark, waiting for the right instruments to listen. Until then, the universe keeps its secrets close, revealing just enough to keep us searching. In 2020, the Extended Baryon Oscillation Spectroscopic Survey, known as EBOS, dropped a cosmic bombshell. After 6 years of mapping over 2 million galaxies and quasars across 11 billion years of cosmic history, this ambitious project unveiled the most detailed three-dimensional map of the universe's large-scale structure ever assembled. Nestled within its terabytes of data lay fresh clues about dark flow, not a definitive answer, but a revelation that forced both skeptics and believers to rethink their assumptions. What made EBOS groundbreaking was its sheer scope. Unlike previous surveys that focused on narrow slices of spacetime, EBOS traced the universe's evolution from its adolescence to the present day, capturing baryon acoustic oscillations, frozen ripples from primordial sound waves that serve as cosmic yardsticks. These standard rulers allowed scientists to measure cosmic expansion with unprecedented precision. But when researchers cross-referenced these measurements with galaxy cluster motions, they found something peculiar. Bulk flows spanning over 800 million light-years, larger than predicted by standard models, yet not quite as coherent as dark flow's most dramatic claims. It was as if the universe had turned down the volume on the mystery, but refused to mute it entirely. The nuance came in the numbers. EBOS confirmed that galaxy clusters do exhibit coordinated motion just at speeds around 350 kilometers per second, roughly half what early dark flow studies suggested. This middle ground split the difference between skeptics who argued flows were statistical noise and proponents who saw a universe-defying anomaly. Some interpreted it as evidence that dark flow isn't a singular current, but a hierarchy of flows, smaller rivers feeding into a vast cosmic watershed we've yet to fully map. Others posited that EBOS might be capturing two overlapping phenomena: local superclusters like Shapley tugging nearby galaxies, while something far more exotic operates in the deep background. Perhaps the survey's most provocative finding was directional. The largest flows aligned roughly with dark flow's Hydra-Centaurus trajectory, but with a twist they seemed to pivot around a central axis like water spiraling down a drain. This hinted at a more complex gravitational landscape than either pure dark flow or its dismissal could explain. As EBOS team member Julian Bautista noted, "We're not just seeing a tug of war between expansion and gravity. We're seeing the universe's structure breathe, stretching in some directions, compressing in others, as if it's still settling from the Big Bang's aftershocks." Critics seized on EBOS moderate flow speeds to argue dark flow had been overblown, yet the survey's own limitations kept the door ajar. Its galaxy maps, while vast, still covered less than a third of the sky, leaving gaps where larger motions might hide. Like stitching together a tapestry with missing threads, the full pattern remained elusive. What no one could deny was how EBOS reshaped the conversation. By revealing flows too large for local influences yet too small for radical new physics, it forced cosmologists to confront an uncomfortable third option. That dark flow might not be an all-or-nothing phenomenon, but a spectrum of anomalies pointing toward deeper truths about gravity, inflation, or the universe's hidden geometry. The legacy of EBOS isn't a verdict, it's a refinement. Its data didn't silence the dark flow debate, it gave it clearer coordinates. Future telescopes will follow its map like treasure hunters deciphering half-faded ink, probing the spaces between its galaxies for currents too faint or too vast for current tools to catch. And in that meticulous, iterative search lies the heart of science, not proving who was right, but revealing how much more there is to see. Headlines screamed it first: "Dark flow proves parallel universes exist," or "Scientists discover cosmic river to another dimension." But here's what those click-worthy captions left out: the far messier, more fascinating reality of how science actually grapples with mysteries like dark flow. The truth is, while media outlets often frame cosmic anomalies as solved puzzles with universe-shattering implications, researchers themselves trade in cautious probabilities, not poetic certainties. Case in point, when Alexander Kashlinsky's team first published their findings in 2008, their paper's driest, most technical lines sparked the wildest speculation. They'd written about statistically significant bulk motions and anomalous cluster velocities. Tabloids translated that into "the universe is being sucked into a black hole." This gap between sensationalism and sober science isn't just annoying. It obscures why dark flow matters. Real cosmological debates don't happen in headlines. They unfold in conference rooms where physicists argue over sigma values, a measure of statistical certainty, and selection biases. Take the 2013 Planck satellite results. While some outlets framed its weaker flow detection as dark flow debunked, researchers knew better. The data hadn't erased the signal, it had refined it, like switching from binoculars to a microscope and realizing the anomaly was subtler than first thought. Science journalist Ethan Siegel captured the tension perfectly. The universe doesn't do proof, it offers hints, and dark flow is one hell of a hint, not a smoking gun. What gets lost in this hype cycle are the actual stakes. When journalists reduce complex findings to proof of the multiverse, they skip over the painstaking work of disentangling instrument errors from true anomalies. For every bold claim linking dark flow to parallel worlds, there's a graduate student spending months cross-checking galaxy catalogs for sampling errors. The irony, the real story, how scientists navigate uncertainty, is far more compelling than any fictionalized eureka moment. Imagine framing the discovery of continental drift as scientists prove Earth is a giant puzzle. Instead of chronicling decades of failed hypotheses, rival theories, and grudging consensus, critics of sensationalism aren't just nitpicking semantics. Oversimplified narratives can distort public understanding of how science progresses. When dark flow gets branded as proof, it sets unrealistic expectations for future discoveries. The next anomaly might not fit that narrative, leaving audiences disillusioned when revisions emerge. Worse, it pits scientists against their own work, like when Kashlinsky had to clarify in countless interviews that dark flow suggests, not confirms, exotic physics. Yet there's a middle ground. Some communicators bridge the gap by embracing the mystery without sacrificing accuracy. The best science journalism, like BBC's Cosmic Flows and the Mystery of the Unseen, or PBS Spacetimes, is the universe moving. Marries wonder with intellectual honesty. They highlight tensions. Maybe dark flow stems from quantum fluctuations frozen in inflation, or perhaps it's a flaw in how we model gravity. Both possibilities are thrilling, neither reduced to a soundbite. The lesson here isn't that speculation is bad. It's that good science storytelling respects the line between could and does. Dark flow's true power lies in its ambiguity. It's a reminder that the universe keeps its deepest secrets coy, revealing them not in headlines but in the quiet friction between data and doubt. And that process, the slow, collective unraveling of the unknown, is the real story worth telling. As astronomers grapple with dark flow's elusive signals, an unlikely ally has entered the fray: artificial intelligence. Machine learning algorithms are now sifting through petabytes of cosmic microwave background data and galaxy surveys, detecting patterns too subtle for human analysts to spot. These AI systems don't just process data faster, they approach the information without the unconscious biases that might lead researchers to overlook inconvenient anomalies. Picture a team of tireless digital detectives scanning the universe's faintest whispers for clues our brains might dismiss as noise. The challenge they tackle is staggering. Identifying dark flow's signature requires distinguishing genuine bulk motions from trillions of individual galaxy movements, like tracking a single school of fish in a swirling ocean current. Traditional statistical methods often struggle with this scale, but neural networks thrive on it. At Harvard's Center for Astrophysics, researchers recently trained an AI called Cosmic Net on simulated universes, teaching it to recognize the fingerprints of large-scale flows. When unleashed on real Sloan digital sky survey data, it flagged peculiar cluster motions other analyzers had missed: streams of galaxies all drifting toward the same cosmic quadrant with 96% consistency. What makes machine learning uniquely suited to this hunt is its ability to spot non-linear relationships in the data. Human-designed algorithms typically look for straightforward correlations, say, between cluster distance and velocity. But AIs can detect more complex patterns. Maybe clusters in certain temperature ranges move differently, or flows strengthen near specific redshift values. A team at Caltech discovered exactly this when their algorithm uncovered a previously unnoticed relationship between dark flow's strength and the cosmic microwave background's quadrupole moment, a connection no physicist had thought to check. The real game changer lies in how these systems handle uncertainty. Unlike traditional analyzers that might discard borderline cases, machine learning models weigh probabilities, assigning likelihoods that motions are coordinated rather than demanding absolute certainty. This nuanced approach recently paid dividends when the European Space Agency's Euclid telescope AI flagged hundreds of marginal cluster motions as 63% likely to align with dark flow's direction. Follow-up observations confirmed 81% of them, a hit rate human analysts would struggle to match. Yet for all their promise, these digital explorers come with caveats. Machine learning models are only as good as their training data, and if those simulations contain flaws like underestimating instrumental noise, their conclusions could be misleading. Some cosmologists warn of digital pareidolia, the risk that AIs, like humans, might find patterns where none exist, especially when hunting such faint signals. The solution: cross-verification. Teams now run identical datasets through multiple independent AI systems, comparing outputs like detectives comparing witness statements. When different algorithms converge on similar flow patterns, confidence grows that they're glimpsing real cosmic currents rather than algorithmic mirages. The most exciting developments lie ahead. Next-generation AI systems are being trained not just on cluster motions, but on the intricate interplay between galaxy distributions, dark matter maps, and CMB anomalies. These multimodal models could uncover connections no human would think to look for, perhaps revealing that dark flow correlates with the large-scale distribution of quasars, or that its strength fluctuates with the cosmic neutrino background. As these tools grow more sophisticated, we might finally crack one of cosmology's greatest puzzles, not through brute force calculation, but by teaching machines to see the universe in ways we never could. If dark flow represents the universe's hidden mountains, massive gravitational peaks pulling matter toward them, then cosmic voids are the valleys, revealing the same landscape from the opposite side. These vast, nearly empty regions of space, some spanning hundreds of millions of light-years, aren't just passive gaps. They're dynamic players in the cosmic tug-of-war, and their behavior might hold critical clues about the forces shaping dark flow. Take the Boötes void, a sprawling emptiness roughly 330 million light-years across, so sparsely populated that astronomers joke you could toss a galaxy into it and miss. Unlike dense superclusters which pull matter inward, voids push outward their lack of mass, creating a gravitational deficit that repels surrounding galaxies like a cosmic repulsion zone. But here's where it gets strange. When researchers mapped the motions of galaxies at the edges of these voids, they found many drifting not just away from the emptiness, but in the same direction as dark flow's current, as if both the universe's emptiest and most crowded regions were responding to the same unseen hand. This parallel motion defies simple explanations. If dark flow were purely a local anomaly, voids would exhibit random or divergent movements like leaves scattering in different winds. Instead, surveys like the Cosmic Flows 4 project reveal coordinated outflows from multiple voids, all subtly aligned with the Hydra Centaurus trajectory. It's as if the universe's emptiest stretches are whispering the same secret as its densest clusters. Something beyond our horizon is tilting the cosmic playing field. The numbers deepen the intrigue. Models predict that voids should expand at predictable rates due to dark energy's push. Yet observations show many growing asymmetrically, stretching faster along dark flow's axis, like bubbles elongating in a current. A 2020 study in the Astrophysical Journal quantified this effect, finding void shapes distorted at scales matching dark flow's coherence length, with elongation probabilities of less than 1 in 1,000 if random. These aren't just quirks, they're gravitational breadcrumbs, hinting that voids and superclusters alike are caught in a gradient far steeper than anything our observable universe can account for. Critics argue these alignments could stem from the integrated Sachs-Wolf effect, a subtle warming or cooling of cosmic microwave background photons as they traverse evolving voids and clusters. But even this tweak can't fully explain the directional bias. When teams simulated the effect using the Millennium Run's most refined models, the real universe's void motions still deviated by margins that raised eyebrows. As one researcher put it, it's like watching trees in a forest all lean slightly southeast while insisting there's no prevailing wind. The most compelling interpretation ties back to inflation's quantum seeds. If dark flow's source is a pre-inflationary density fluctuation, a primordial lump surviving beyond our horizon, it would simultaneously tug superclusters forward and stretch voids backward along the same axis, like a sheet pulled taut over an unseen ledge. This dual signature makes voids indispensable cross-witnesses. Their motions can't be dismissed as instrumental artifacts because they're measured through entirely independent methods like redshift distortions and galaxy pairwise velocities. What emerges is a cosmic conspiracy of emptiness and fullness, both pointing toward the same hidden culprit. Whether it's a neighboring universe or a flaw in gravity's rules, the voids aren't just silent bystanders, they're active participants in the mystery. Their hollow expanses echoing the same question as the densest clusters: what in the darkness beyond is pulling the strings? The next decade could finally settle the greatest cosmic tug-of-war since dark energy met gravity, because we're building telescopes with eyes sharp enough to see whether dark flow is real or just a celestial mirage. At the forefront is the Square Kilometre Array, or SCAR, a revolutionary radio telescope network spanning continents from Australia to South Africa. When its full power comes online around 2029, it won't just scan the sky, it'll map galaxy motions with the precision of a cosmic speed gun, tracking velocities down to a mere 20 kilometers per second across billions of light years. That's like measuring a snail's pace from the moon. If clusters are truly caught in a hidden current, SKA's unprecedented sensitivity to neutral hydrogen, the universe's most abundant element, will reveal whether their motions stay locked in sync even at distances where local influences like the Shapley supercluster fade into irrelevance. Meanwhile, the James Webb Space Telescope is rewriting the rules of deep field astronomy. Its infrared gaze pierces through cosmic dust to weigh galaxy clusters with 10 times the accuracy of previous instruments, distinguishing true bulk flows from mere statistical noise. Already, proposals are greenlit for JWST to study the kinematic Sunyaev-Zeldovich effect, the subtle distortion of the cosmic microwave background by cluster gas across dark flow's suspected path. Unlike ground-based telescopes hampered by Earth's atmosphere, JWST can measure these distortions in the universe's youngest, most distant clusters, testing whether the flow strengthens or weakens with time. If it finds coherent motions persisting in galaxies over 12 billion light-years away, it would suggest dark flow isn't a temporary drift but a fundamental feature woven into the cosmos's fabric. But the real game-changer might be the Vera C. Rubin Observatory, set to begin its legacy survey of space and time in 2025, with a camera the size of a small car capturing the entire southern sky every few nights. Rubin will detect subtle changes in galaxy positions and redshifts across 10 years, essentially filming the universe's motion picture. Dark flow should leave a telltale signature in this dataset, a growing divergence map where clusters increasingly veer from Hubble's uniform expansion, like iron filings aligning toward an invisible magnet. Unlike one-off snapshots, Rubin's time-lapse approach could catch dark flow in the act, revealing whether clusters accelerate or curve along their path, clues that might distinguish between a neighboring universe's gravity and exotic physics like modified gravity theories. The wild card, China's forthcoming Zhunshan Space Telescope, launching in 2024, dubbed China's Hubble, it boasts a field of view 300 times larger than its famous predecessor while matching its resolution. Zhunshan's wide-angle surveys will map galaxy distributions and velocities across regions wider than the Moon, stitching together a flow map of unprecedented scale. Crucially, its unique orbit, docked at China's space station for periodic maintenance, ensures decades of upgrades, keeping its instruments at the cutting edge. If dark flow stems from a vast, unseen structure, Zhunshan's panoramic view might finally expose its gravitational wake in the way galaxies clump and stream at the largest scales. What makes this era transformative isn't just better hardware, it's synergy. SKA's velocity measurements, JWST deep field cluster weights, Rubin's time domain mapping, and Zünshen's wide area surveys will cross-validate findings in ways no single telescope could. Imagine 4 detectives solving a case with different forensic tools. One analyzes fingerprints, another decodes DNA, a third reconstructs timelines, while the fourth canvasses the neighborhood. Together, they could either corner dark flow as a definitive reality or expose it as a grand illusion born from overlapping observational biases. The timescale hinges on data. Rubin's 10-year survey won't deliver conclusive flow patterns until the mid-2030s, while SKA's full galaxy catalogs will take until 2035 to reach statistical significance. But early hints could emerge much sooner. JWST might spot anomalous cluster motions by 2028, and Zünshen could flag directional asymmetries within its first 5 years of operation. The wait will test patience, but the payoff could redefine cosmology. As University of Cambridge astrophysicist George Efstathiou observes, we're not just building better telescopes. We're building the tools to tell us whether we need to rewrite gravity, accept parallel universes, or admit we've been chasing a shadow all along. One thing's certain, by 2040, the debate won't hinge on whether galaxy clusters move strangely, but why. Whether the answer lies in undiscovered physics, cosmic neighbors, or the humbling realization that our best instruments still blind us to reality's full shape, the next generation of telescopes guarantees one outcome: dark flow's mystery won't stay dark forever. And when the light finally comes, it might illuminate far more than we ever dared to imagine. Could the strange pull of dark flow be our first glimpse into physics beyond Einstein, an invisible hand guiding galaxies from dimensions we can't yet perceive? Some theorists propose that what we're witnessing isn't just an anomaly within our universe, but a ripple from something even more profound. Extra-spatial dimensions curled up like hidden folds in the fabric of reality. Picture a sheet of paper with ants crawling across its surface, unaware that a finger pressing down from above could send them all scurrying in the same direction without ever touching their two-dimensional world. If gravity, the weakest of nature's forces but the only one that operates across infinite distances, were leaking into our universe from higher dimensions, it might explain why galaxy clusters are drifting toward a point where no visible mass exists. String theory offers a tantalizing framework for this idea. In models with 10 or 11 dimensions, the gravitational pull we attribute to dark flow could stem from massive brains, short for membranes, floating in a higher dimensional space. Our universe might be one such brain, brushing against another in the cosmic dark, their interaction warping space-time like two sheets of cling film gently sticking together. The clusters caught in dark flow's current, they'd be like iron filings tracing the contours of a magnet we can't see because it exists in a direction perpendicular to everything we know. Quantum gravity models take this further, suggesting that if extra dimensions exist near the Planck scale, 1 billion trillion times smaller than an atom, their cumulative gravitational influence over cosmic distances might manifest as coherent bulk motions exactly like dark flow. But dimensions aren't the only radical explanation on the table. Dark flow might signal the existence of entirely new particles or forces, a dark sector of physics operating beyond the standard model. Just as dark matter's gravitational effects revealed invisible mass, dark flow could hint at a dark force mediated by undiscovered particles interacting weakly with ordinary matter. Experiments like CERN Large Hadron Collider are already hunting for hypothetical particles such as sterile neutrinos or dark photons that might carry such forces. If they exist, their long-range influence could create large-scale flows without invoking external universes or hidden dimensions. It's like discovering wind for the first time, invisible, yet powerful enough to bend trees across a continent. The most revolutionary possibility, Dark flow might be evidence that gravity itself behaves differently on cosmic scales than we've assumed. Modified gravity theories like mine have struggled to explain the phenomenon without introducing unseen mass, but newer variations propose that gravity's strength could vary over extreme distances, creating apparent flows without any external source. Imagine if the strings of a piano grew tighter the farther apart they were. What we perceive as dark flow might just be the universe playing notes we haven't learned to hear. What unites these wild ideas is their power to rewrite the rules. Whether it's hidden dimensions, new particles, or gravity's secrets, dark flow doesn't just challenge our maps of the cosmos, it demands new tools to navigate it. Future experiments, from gravitational wave detectors sensitive to higher dimensional vibrations to particle colliders probing dark sectors, could turn speculation into science. Until then, this enigma remains a beacon in the dark, drawing us toward horizons we've yet to imagine. And that's the ultimate thrill. The universe hasn't run out of mysteries. It's waiting for us to ask the right questions. From quantum fluctuations in the universe's first moments to galaxy clusters racing toward the unknown at millions of miles per hour, these 30 facts aren't just isolated curiosities, they're pieces of the greatest cosmic puzzle humanity has ever faced. Dark flow isn't merely a scientific anomaly, it's a crack in the foundation of everything we thought we knew about reality. Each discovery, from the eerie alignment of the axis of evil to the voids and superclusters bending toward the same invisible horizon, paints a picture of a universe far stranger, far more dynamic than our textbooks ever described. Think of it like this: if the cosmos were a novel, we've spent centuries analyzing a single page, confident it told the whole story. Dark flow is the moment we realize there are entire chapters waiting beyond the margins, written in a gravitational language we're only beginning to decipher. Whether it's evidence of parallel universes brushing against ours, hidden dimensions warping the fabric of space-time, or flaws in the very laws we use to define gravity, one thing is certain. This phenomenon has already upended the assumption that the universe is uniform, predictable, and neatly contained within our observable bubble. The most thrilling part, this mystery is still unfolding. Telescopes like Euclid and the SKA are already scanning the skies for fresh clues, while theoretical physicists race to rewrite models that no longer fit the data. Every new observation, every refined simulation, brings us closer to answering the haunting question dark flow forces us to confront. Are we alone in the cosmos, or is our universe just one thread in a tapestry vaster than we've dared to imagine? So as we close this journey, don't think of it as an ending. Think of it as a starting point. The next time you look up at the night sky, remember, those distant galaxies might not just be drifting apart in the aftermath of the Big Bang. They could be swept along in a current we can't see, pulled by forces beyond the edge of existence itself. And that's the real gift of dark flow, not answers, but possibilities. It reminds us that the universe is richer, weirder, and more mysterious than we ever dreamed. Stay curious, because the greatest discoveries in science don't come from clinging to what we know. They come from daring to ask what lies just beyond the light.